Welcome back to our Unit 2.6 recap. At this point we're looking at binary, denary and hexadecimal number systems and how they relate in computing. Now, denary is our normal number system. It's the one that you're used to. It's a base 10 number system, which means that it has 10 options. In a single column, there's 10 different things that you can write in there, all the way up to 9 as our highest value and starting from 0. So 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. Those are our 10 options for denary. I say it's our normal number system. It's the one that you're used to. It's the one that right from an early age, your beginning of your career in school, you learnt that it's all about the units, the tens, the hundreds, the thousands, that sort of thing. So the number 108 has got 100, it's got no tens, and it's got 8 units, giving you 108 in total. I don't need to tell you how to do counting in normal numbers. You know well and good. So each of these columns is 10 times bigger than the previous column. We're going to do exactly the same thing for binary and hexadecimal. Our binary number system, let's use blue for binary, is what computers use. So it's not the normal number system, but computers, remember, can use only transistors which are either on or off, a 1 or a 0. And so they need to do all of their counting, all their maths, all their everything using only 2 options. So it's a base 2 number system, and we've got only 2 options per column, 0 and 1. Now, instead of multiplying by 10 each time that you come through this, binary multiplies by 2 because it's a base 2 number system. So we start with our units and then multiply by 2 gives us 2. Then multiply that by 2 to get 4. So units, 2s, 4s, 8s, 16, 32s, 64s, 128. To be honest, at GCSE you never need to go beyond 8 binary characters. And you could have something like 0, 1, 1, 0, 0, 1, 1, 1. A string of 8 binary digits. But what would this mean? Well, you can see all of these different place values. You've got a 1, you've got a 2, you've got a 4, you've got a 32, and you've got a 64. And you can add those up together. So 64 add 32 is what, 96? Add 4 is 100, add 2 is 102, and add the 1 for the unit there, and you've got ourselves 103. Okay, let's move on to hexadecimal. Hexadecimal is something that computers use, or computer scientists use, as a quick and easy way of noting down a long binary string. And we can go through later how these 1s and 0s can easily be translated and memorized for hexadecimal. So programmers only use it as a way to remember what's going on in binary. It's very difficult to remember a lot of 1s and 0s. It's easier to remember just a few letters and numbers in hexadecimal. Now, I say letters because we've got a base 16 number system for hexadecimal, which means each column can have 16 different options in it. The 10 that we're used to, plus some extra ones. And because we've run out of numbers, we then have to use letters. A, B, C, D, E, and F. And so these represent 10, 11, 12, 13, 14, and 15. So we've got 16 different options that we can use in hexadecimal. So instead of multiplying by 10 each time like we did for base 10, and instead of multiplying by 2 each time for our column place value, like we did with binary, we're going to have to multiply by 16 this time in hexadecimal. So we've got our units, and then we've got our 16s, and then, well, 16 times 16 is 256, so we've got our 256 column, but again, for GCSE, you'll only ever encounter a 2-digit hexadecimal value. Let's give ourselves a bit of a hexadecimal value to try and work out the base 10 equivalent of. Base 10, we had 108 just here. We had 0110, 0111 in binary, which we worked out was 103 as a base 10 value. And over here, let's give ourselves something like 6C. So 6C means we've got 6 16s and then C units. But what is C? Well, let's look it up. C is 12 because we can count up from 9. So we've got 12 units, which is just 12. 6 16s are 60 plus 36, so that's 96. 96 add 12 is, oh, look at that. It's the same as what we had in the middle here, 108. So we've got 96 for the 6 column because it's 6 lots of 16. So its place value makes a huge difference, obviously. Now, there is a beautiful relationship between binary and hexadecimal. As I said, the only reason we use hexadecimal is so that we can remember things that are written in binary. So just down here, I'm going to write a binary string. And I don't know what that binary string is, but it's going to be easy to convert it into hexadecimal. So 11001111. Now, that's 8 digits. And this, I said, can be easily converted into hexadecimal. And what we do is we can split it into 4-bit nibbles. So each 4-bit nibble represents a single digit in hexadecimal. And that should make sense to you because look, we can represent up to 16 different values in just 4 bits, from 0000 all the way up to 1111, which represents 15. Oh, look at that. Corresponds to that. So a single hexadecimal digit is represented by 4 binary digits. So 1111 is our highest number in hexadecimal, which is 15.